final paper for this session is by Dr. Tom Vandenberg, who is he's a physicist and a head of the research unit of the Ocular Signal Transaction of the Netherlands Ophthalmic Research Institute at the Royal Netherlands Academy of Arts and Sciences in Amsterdam in the Netherlands. And the title of this paper is the Straylight Basis of Disability Glare Assessment and Origins. Oh, okay.
Okay, let me go back. Okay, well, first of all, I would like to thank the organizers, Phil and Cynthia, for inviting me here in this very beautiful meeting. It's really a pleasure, and I love the discussions very much. As this slide shows, my presentation is on glare. It's a bit different from the presentations we have been hearing today, because my presentation will be mostly on the basics, maybe a bit fundamental, a bit more concentrated on vision, because that's well, what I do. I'm a physicist, and I'm studying the optics of the eye. I must mention at this moment that the institute I belong to is part of the Royal Academy, and the Royal Academy has a financial interest in something that I will be mentioning at the end, and that's an instrument to measure stray light, which is the basis of glare. Reports and publications on everything that I will be saying you can find on this website. It may be strange that this website is a Belgian website, as you can see, whereas I am located in the Netherlands, but that is because much of the studies is a European consortium result. Well, if we speak about glare, then of course we first must mention that there are two types of glare, and the one type is discomfort glare, which is annoying, which is unpleasant, and there is disability glare. And disability glare is of course the type of glare that we are most worried with, but the other type of glare is also important. But as we will see further on, the discomfort glare often corresponds or follows the amount of disability glare people are sensitive to. But my presentation will be on disability glare, as it impairs the eye's ability to distinguish differences in brightness and color. It produces a reduction in the visibility distance, and that's for driving especially important. It reduces the visibility distance of objects, and it's created by localized lights that are so bright that its intensity results, and it's a very talkative way of expressing what is glare about, its intensity results in a measurable reduction in the driver's ability to perform visible tasks. This gives an overview of my presentation. First, I will mention a few of the glare effects on vision. Of course, we are worried about the effects on vision. What does it do to our visual capacity? And that blinding by disability glare, a safety issue in driving. Then the next topic will be understanding disability glare, and it has been proven, there are much studies about that, that disability glare is caused by a desensitization of the retina by a veil of stray light. And this stray light is real light that drops on the retina because of the glare source, and so glare sensitivity is, as it were, synonymous with retinal stray light. Then I will talk a little bit about the development of assessment technology of Straylight as the basis for disability glare. And in the end, I will just very quickly show the new way of testing, measuring Straylight, as I just mentioned. Well, this is the typical effect of Straylight, and here I must add these are real simulations. These are simulations based on physical knowledge on glare and Straylight in the eye. So this is really what's going on. And you see, for a healthy eye, well, you can still see with a blinding light source, but with early cataract, visibility is lost to a great deal. Glare is not restricted to twilight conditions. Also, during daytime, you can be very much handicapped by it. But it's not only in traffic that we are handicapped by glare. These are the signs in the elevator of our institute, and you can see that, and again, these are real simulations based on the physics of the phenomenon, that the normal 67-year-old eye with a certain normal amount of Straylight already has difficulty seeing the signs in the elevator, but in early cataract, visibility is lost completely. But also, this is a typical complaint of older people that start having problems with light scattering in their eyes. Young normal to the left, well, that does not relate to the person depicted, that relates to the eye that's looking at this person. And the young normal eye would see me like that, but with the first sign of a cataract, if I would sit against the light, you could hardly distinguish the facial characteristics. And this shows in a numerical fashion the problem you have while driving with glare. I have depicted three types of oncoming lights: low beams, the daytime running lights, and high beams. And for a typical, there is a lot of statistics about this. For a typical situation, while driving at night, at the right, you will see the amount of desensitization the eye suffers under the different conditions. And you can see that with low beams, the young healthy eye suffers only a sensitivity loss of a factor of 1.2. But with a little bit of, I've called it preclinical, for the clinic not yet important cataract, it's already a desensitization of a factor of 2. And with mild or medium cataract, it's a factor of 3.4. And if you go down, you can see that at the lower end, with high beams, of course, we are blinded completely. This is complete blinding. You cannot see anything any longer under such a condition. And in such a condition, it is, of course, another aspect, and that's the time aspects of blinding. It will take the older subject and the cataracted subject longer to recover after such a blinding stroke. Understanding disability glare. It is identified as a desensitization of the retina by stray light. And there is a history of studies on that, and I will not go into that to prove that that is really the case. Disability glare is the phenomenon of stray light. And here, a kind of overview of that effect. That the point spread function, if you look at the point source of light, and we as speakers are helped by the organization by looking into such a point source of light. And what I see around this point source of light is light spreading around this. And this is really what happens on the retina. And that is why I cannot see the operators there, because the light that is projected on top of them reduces the sensitivity of my retina, and so I cannot see them any longer. The primary stray light contributors, it's in the normal eye, it's the cornea, it's the lens, but also The sclera and the iris are a bit translucent, adding light scattered on the retina, and back reflection of the fundus is a fourth important component. But it increases in cataract, and of course that has had a lot of attention today, but also in corneal problems, also in refractive surgery, also in vitreous turbidity, and there are a lot more conditions where Straylight increases. To measure Straylight, we made a small instrument some time ago to accommodate colleagues, and in recent years we decided to study in more detail how to best test Straylight in the human eye. The basis of the method is this. It's very simple, very straightforward. What we do present to the subject is a ring of light that is flickering. This ring of light, of course, must be projected on the retina in a proper manner. But the light of this ring of light penetrates the media of the eye, part of it is scattered, and in the central test field, part of that light, because of light scattering, because of stray light, will be projected. And so you will see there in the center light flickering. Well, not in this demonstration, but you can see that later. You will see there your own stray light. And the way to measure it is to give compensation light in that central field. Counterface compensation light. And if you increase the amount of counterface compensation light in that center, then of course you extinguish the flicker that you see. And you use the retina as a null instrument. You null the amount of flicker caused by stray light by adjusting a settable amount of compensation light. And in that way, you find by direct compensation the exact and physical measure of light scattering in your eye. Well, with this technique, we measured glare or stray light in normal eyes. This is an example for normal individuals with very good visual acuity up till the age of 80. But as you can see here, it's highly individual dependent. With early cataract, of course, it increases, but you can see here that the way it increases is much like increased aging, quicker aging. The shape of the function remains more or less the same as for an older age group. And this was the distribution we found among European drivers. And you can see that there is a lot of variation there. But of course, this was just a population that was not screened for not having cataract or early cataract or other problems to the eyes. This was just a sample of the European driving population. Our results on precisely the physical characteristics of light scattering in the eye also gave us the possibility to create simulation models, to create filters, light scattering filters, that precisely mimic the true light scattering properties of cataracts in the eye. And we could do, of course, the same for other parts of the eye, but for early cataracts, that's most interesting. And these kinds of filters then can be used for field studies, for driving studies, but for all kinds of studies on the effects of light scattering or increased light scattering in the eye on visual function. Now back to developing the assessment technology. A few years ago, a study was performed on existing technology, and it was found that stray light measurement, being such a physical measurement, is much preciser, much better reproducible, correlates better with the glare effect than existing glare testing technology. And just a few hours ago, the bed tester was mentioned as a way of testing that does not give results that you can very well use. But for specific driver testing, such a test must fulfill certain demands. It must be easy, it must be fast. Results must not be influenced by the subjects, and there must be, and that was very important, a reliability index. Just as with visual field studies, we know those are very variable outcomes, and you need some test for reliability. And in some visual field testers, there is a kind of a test for reliability, but here we of course needed also a test for reliability. And so we changed the test into what we now call the compensation comparison test. And instead of having one central test field, we now subdivided the central test field in two halves. And in the presence of a flickering ring, then of course flicker exists in both halves of the central test field. But now we changed the setup in giving compensation in only one half of the two test fields. And the subject's task is to compare one half with the other half, which side flickers most. And in this comparison, you can find very precisely what the true Straylight value in that individual is. If compensating light is very high, then of course that side will be chosen as the side that flickers strongest. If compensation light goes down to the level of Straylight of that individual, then the side of compensation is null. There is no flicker any longer, and the other side will be flickering stronger. And this gives a very precise indication of the Straylight value of the individual. So these are the characteristics of this way of testing. It's a two alternative forced choice method. That's very important because with that kind of a method, there is very good psychophysical knowledge and statistical knowledge on how to treat that kind of data, how to analyze that kind of data, how to find a reliability indicator for that kind of data. And there are some other aspects that make it suitable for driver testing. Now this then gives an example of how such a test is performed. Oops, sorry. That again. At first, presentations are given with a very high level of compensation. And then if that level of compensation approaches the true value of the individual, the response of the individual jumps over to the other side. And then the other side of the two halves is being chosen. And then at the end, you can find with the red dot here the Straylight level of that individual compared to the normal population given by those lines. And this is another example of such a measurement outcome. Reliability results were tested by repeating the measurements in a large group of subjects twice and to compare those repeated measurements with the predicted, from this psychophysical technique, the predicted reliability value. And you see here the outcome showing that the accuracy of this method is very good and more than enough for such a thing as driver licensing, but of course also to be used in ophthalmology to give objective value to complaints of patients. Here the reliability is compared to the differences found in the European population. The column size in these graphs has the width of the repeatability of this measurement, and you can see that you can very good differentiate between the different within as well as between the different age groups. And with this I end my presentation. The instrument, so there was a firm in Germany that thought this was nice to make it into an instrument. And I have brought that instrument for you to see and to measure your own eye. It's in the back of the room, and maybe during lunchtime tomorrow or during the breaks, I will be more than happy to show it to your own eye and to measure your own eye if you would be interested in that. I thank you.
Thank you. Are there any questions?
Cynthia Ousley, is this on? Okay. I just had a question about the impact of the retina on the response that the patient gives. I'm over here.
Yes, I know.
Oh, okay.
Oh, sorry.
I'm over here.
I thought that Sheila was getting... Okay.
I'm sorry, because, what am I trying to ask here? Because desensitization of the retina is the mechanism, you're not only going to have patients with different anterior segment... Okay, you're going to have patients with different anterior segment characteristics, but your patients are also going to have different retina. There's going to be a lot of individual variability, especially in older adults, in the processing capabilities, the disease state of the retina. And I was just wondering if you could comment on the impact of that variable in your test and whether that's divided out of the response, or how do you take that into account?
Well, in the Straylight measurement itself, you must, so what we do is we have light scattering in the eye from the ring, so that's really light that's dropping on the fovea. Yes? And what we then do in the center of that ring, we present counterphase light, so that goes on if the ring goes off and reverse. And both lights scattered in the eye, reaching the fovea and being projected directly on the fovea, are summed in the fovea. And so we have there two lights. At first, it's only the scattered light. And then if we add the compensation light, that goes in the opposite way. The sum of these two will be 0. The fact that that is 0 is independent of the condition of the retina. The retina is used as a null instrument. It only needs to be capable of seeing low frequency flicker. It's a flicker of 8 Hertz, 100%. Everybody can see that. And also people that have diminished flicker sensitivity will have the same moment when those two lights are equal. That moment does not change by the condition of the retina. Only the precision by which you can judge 0 flicker, that precision will be hampered. But in the psychophysics of this, this test, we can see that. We can see the accuracy that the patient has. And so it's a null instrument, the retina. Its sensitivity is not involved.
So just to make sure I understand then, if we have two patients with identical anterior segments, I know that never happens,
Yes.
but two
Sure.
identical anterior segments, but one patient has intermediate AMD and the other patient is normal retinal health, the instrument would indicate the same amount of stray light.
Exactly the same amount, yes.
Yeah,
Sorry,
now,
yes.
now me.
Now Sheila.
I mean, this is really, really interesting. And as I alluded to in the talk, the patients who were complaining of glare and who stopped night driving were still performing adequately on the old glare tester that we had. I'm just wondering what the correlation is with complaints or symptoms of glare along with the machine that you have.
Yeah. Well, in the earlier study, when we decided to make something that would be useful for large use, that was precisely the problem. We tested their glare testers for a driving situation, and we found that precisely as you showed, there was no correlation with the complaints, and also it did not even clearly separate out clear cataract patients from non-cataract patients. And well, there is a lot that we could say about that, because of course we thought about how to understand that for glare testers. And so and we decided to do that. But I think it's a large and partly speculative story to be said about that.
Does the pupil, you're doing the test at near. Does the pupillary size make a difference?
Not too much. It, of course, will depend on the precise type of cataract or turbidity that you do have, because it kind of averages out over the pupillary area the average amount of light scattering in that media. But the intention of the instrument is, of course, to give you a figure that you would have during daily activity. That would be the amount of light scattering, the amount of stray light that you would suffer from in daily activity. So we chose for an instrument that gives about a 4 millimeter pupil. But in practice, that's not a very big effect. The fact that during night driving people are more hindered by glare is not so much because the size of pupil has something to do with it, but has much more to do with the lighting conditions at night.
At night no, you have... It has much more to do with where the cataract is. If the cataract is posterior subcapsular cataract, then they're crippled.
Precisely. That was mentioned earlier, that people that have posterior subcapsular cataract tend to have more problem with that than with an equivalent type of nuclear or cortical cataract. And that is precisely because of the light scattering properties it has.
Can I make a comment? I think the instrument is really ingenious. I really want to congratulate you on it. This disconnect between a patient's symptoms and complaints and the objective tests that we were talking about. One of the things that I'm finding in my practice is when I ask a patient, do you have trouble at night with oncoming glare? Even the young ones complain. And when I say, well, how old is your car? Then I find out that if the car is new, the complaints are less. And what it ultimately winds up is, we're talking about the health of the windshield. Because when I ask a patient that has an old car, what happens when they rent a new car? They say, oh, well, I'm not that bothered. So I think one of the elements of the disconnect between the cataract and the complaints and the objective tests is that in the car you've also got the windshield.
Yeah, absolutely. That's absolutely true.
Oh, a windshield that's pitted or scraped or dirty, scatters a lot more light and really bothers you when the oncoming headlights.
Not an inherent change in the glass.
No. It's the surface that's over the years gets pitted,
It's dirt.
dirty, pitted, scratched, etc. Actually a big element.
Yeah.
We wash our windshields there.
Yeah.
Oh, whoops. Am I glad I came to this meeting?
We also studied glasses of individuals, and also glasses can be dirty. And there was a nice finding there, and that was that, as a rule, people accept dirtiness of their glasses up to a level, and that level corresponds more or less to the straylight in their own eyes. They do not want their glasses to be dirtier than their own eyes. And I guess that kind of the same might happen in cars.
Okay. Okay, well, this is the end of that session. If you'd like to join me in thanking our 3 excellent speakers, and we reconvene at 3 o'clock for our last paper of the afternoon.